And we're back with part 2. So we'll wrap this standard up and look at question number 28. It says, if the bodies of present-day bats became fossilized over time, which observation would future scientists likely make about the wings of fossilized bats and pterosaurs? Okay, so let's see what we got. Option 1. A comparison of the bones of both organisms would show that the pterosaurs were better suited for flight than bats were. They both fly, and I'm not really sure what about fossils would make the pterosaur look better than the bat. They are both capable of flight, and their bone structure, as we saw up above, is fairly, well, it's the same, but it's got some pretty significant differences in it too, so I'm not really feeling that one. Option 2, the bat wing bones would show a completely different structure than the pterosaur bones. I literally just said they're similar, so that one's not working either. Option 3, both sets of fossils would show similar structures and bone material that were suited for flight. That sounds pretty good because they are similar, not identical, not completely different, and they are obviously wings and made for flight. So that one's my favorite so far. Option 4, both sets of fossils would show that the animals were not designed for a lengthy, sustained flight. Not true. Some of these have migrating paths that they take, and I'm not liking that one either. This one's definitely going to be C as your answer choice. It makes the most sense. It's supported by what we saw above in the other paragraphs. This one is definitely C. And 29 is our next one. Oops, no, it's not. Just kidding. And our next one is number 30. It says, which factor might limit the knowledge of scientists about the role of pterosaur muscles in flight? This is another one of those questions that gave us a ton of information up above. Let's see what it gave us and if it may help us with limiting factors on muscle knowledge. We've kind of skimmed through this before already in previous videos, and we know that the top paragraph is mostly about wing loading and how heavy pterosaurs were. Second paragraph literally starts off about fossil evidence, but right in here is where it gives us actual useful information. It says, although muscles are not preserved in fossil records, there is evidence of their size and strength in the areas where they attach to bones. So let's see if that's going to be useful to us and help us answer this question. All right, what might limit the knowledge? Well, as far as muscles, they didn't preserve and fossilize well, so let's see if we have an answer that lines up with that. Muscle tissues of prehistoric animals were very different from those of modern animals. We kind of don't know how very, very different or alike they were. We can approximate what they looked like, their origins, their insertions of where they would attach to bones, but odds are they probably weren't very different. That's one of those words that you kind of have to key in on, and it can kind of push one true or false. Let's check out other answer choices and see if we have a better one. The number of examples of fossilized bones is greater than the number of fossilized muscle tissue samples. That sounds exactly like what we read about in the paragraph. Let's double check the other two just in case, but I'm pretty sure we found our answer here. The evidence suggests that pterosaurs rely much less on muscle strength and more on bone structure. The muscles are what move the bone, which is essentially what's going to allow you to fly. The bones themselves are going to help be a scaffold for the wings, so Last but not least, the evidence is inconclusive, even though many examples of fossil muscles have been found by scientists. I'm sorry, but when you just hear the word fossil, first thing that probably pops in your head is like dinosaur bones. Rarely ever you're like, oh, I just loved looking at that picture of that fossilized calf muscle. I'm like 99% sure that's never ever happened and probably won't ever happen in my class. So definitely not. B here is your answer choice. 31 is going to be our next standard. It says, which materials would most likely be used by designers of ornithopters to mimic the bone structures of pterosaur wings? Now, it told us that muscles weren't preserved well, but let's see if it gave us any hints in the paragraph as to what the bone structure might be like. Again, looking at that second paragraph, it says this efficient and sustained flapping occurred because pterosaurs had strong muscles and a rigid bone structure. And rigid again means it's not going to flex. It's going to be, well, rigid. So let's see if we have an answer choice that matches any of that. So we have wooden replicas of bones to create identical structures for the devices. Sure. Wood is rigid, but let's double check the other answer choices just to see if we don't have anything better than that. Lightweight metals, an open space structure for the wings. With open space structure, that makes it sound like it's trying to mimic the hollow bones of modern birds, and that's probably going to be more flexible and bendy than what the pterosaur ones would have been. Option 3, heavy metals to prevent bends and tears in the wings. Yeah, I'm definitely not thinking it's going to be that one. Those would certainly be rigid, but you typically don't want to associate the word heavy with trying to make something fly. And last but not least, we've got plastic replicas of bones that have completely filled in structure. That plastic is going to be one of the more lightweight materials that can be used, but because it's filled in, that's going to make it more rigid and less likely to bow and flex. So out of the heavier, rigid options, plastic sounds like that's going to be the way to go, and what's going to be able to give them a more realistic ornithopter to mimic these pterosaur wings. So that is your correct answer there. All right, we've got our next one here with number 42. A data table shows a section of a gene from 4 animals. Based on the partial gene segment, which pair of animals will produce the most similar proteins? So since we're looking for similar, look for the similarities. It's that simple. Don't worry about what gene it's from. Don't worry about what a partial gene segment means. Just look at the similarities here. So we've got AAG for the first 3 and then AAA down here. So gorilla knocked out. We've got GAC, all those match. Here we've got TGG and another TGG. More matching, not exactly, more matching. That one, the chimpanzee, got thrown out because even the chimpanzee and gorilla don't match up right here. So it's going to be our rat and mouse, and that is answer choice number 2. Simple as can be. Don't overthink it. Sometimes they really are as easy as they seem. Sometimes I know that seems like a trap or a trick, but I promise you, just take the nice freebie points on that one. And last but not least, we have question 51. It says, this cladogram shows several animal species. Which adaptations belong with labels U and Y on the cladogram? With cladograms, basically what each of these letters represent are some type of adaptation or trait that everything is going to end up having. So everything, whatever X is, everything above it will have that trait. Whatever Z is, only this will have that trait. So we need to look at where U is and where Y is and see what these organisms have in common. And our options are 6 legs, 2 legs, 8 legs, and antenna. So looking at U, does everything above you have 6 legs? Looks like we've got an ant, 6, grasshopper, 6, fly, 6, dragonfly, 6, and a butterfly, 6. That checks out. The 2 legs is a no-go. 8 legs, only the spider is going to have it. And as far as antenna, that one looked promising because we've got antenna, antenna, antenna. I think dragonfly have antenna, but this picture is kind of terrible, so I can't really tell. And then antenna. So if you wanted a second option to choose from, it looks like your first one and your fourth one look pretty good. Then Y, everything above Y, what they have in common. So segmented wings or 2 wings. Well, you can see here we've got 4, and here we've got 4 wings, so it definitely isn't 2 wings. So the segment of 2 layers of wings, it's definitely A. But this is how cladograms can be useful. I know I didn't get a chance to really go in depth with those in my videos because it's hard to draw on my laptop and explain all this. It's so much easier in person on my smartboard. But I did upload 2 videos, so hopefully you guys are able to watch those because they explained them pretty well in there. And that's it on this topic. Appreciate you guys hanging in there for another part 2 one, and I'll see you with another one of these life science standards in a little bit. See you.